Hello. Today I want to explain to you the difference between chemical structures and a basic understanding of what all of these lines mean. So when we look at organic structures, we see multiple lines, such as in this. If we look at this right here, we would have simple ethanol, which is found in alcohol, such as beer, wine, and liquor. So when we look at a more deep understanding, what do all of these structures mean individually? So, for the first one here, this is a basic CH3, which is a carbon bound by 3 hydrogens. As well, we have another bent angle here that is actually a CH2. So the reason that there are 3 hydrogens on this group is because as a carbon, there can only be 4 bonds to one centralized location. So on the sides we can see there would be 3 hydrogens here, and since this carbon is bound to another carbon and an oxygen, that means that there can only be space for 2 hydrogens on each side. So then our final group on this side of our ethanol molecule is an alcohol group, otherwise known as hydroxyl. This is important because it is a polar element that can be added into many chemical structures in order to create polarity, which we will discuss in another section. Another form of group is something called a carbonyl. So a carbonyl is described as a carbon, which as we see here, bound to an oxygen through a double bond. So in this case, we would question, is there a hydrogen here or not? The answer is there can be a hydrogen here, possibly, right? But if we have just another methyl here, then we would end up having 0 hydrogens around this carbon. Now, how is that possible? The reason it's possible is because we are bound to 2 carbons here, localized to the central one, as well as double bonded to an oxygen up here. So this group is the carbonyl. Specifically, this is a ketone. The reason it's a ketone is because it is in between 2 carbon groups. Go ahead and leave you guys a note here, as it is a ketone. The difference in carbonyls has about a 3-fold difference in generality. So when I say 3-fold, I mean that there are 3 common carbonyls that we will see. This is known as an aldehyde. The reason this is important is because, as you see, this hydrogen is now bound to the carbon, and it is usually a terminal form of molecule. However, it can also be added to other forms of organic compounds as well. It is more polar since it has hydrogen bonding from this, as where when we have a ketone, there is simple nonpolar bondings on each side. Explain more about polarity in a future video, but for now, let's find out what the third molecule is relative to the carbonyl. The third one is a carboxylic acid. Now, what is a carboxylic acid? That is a carbonyl, so carbox. Then as you see right here, the hydroxyl, so carboxyl, then the hydroxyl group here is an acid. What that means is that it acts as a hydrogen donor to bases, which we will explain as well in future. So the rest here is carboxylic acid. So these are the 3 generic different types of carbonyls that will be found in organic chemistry. Let's look at an example of an amine. What is an amine? When you see an N, that is denoted as nitrogen, and one common amine that people all know about that smells really bad is ammonia. So the reason that this is an amine is because there is a nitrogen group bound to either some carbons, some hydrogens, and organic chemistry is as simple as adding just groups two different elements. So if we were to take this and we wanted to look at some other form of amine, we could just add a carbon and look at this. This would be considered methylamine. Now the reason as well that we should look at amines is because there are free electrons here. That is because of the place on the periodic table where it stands, as carbons can have 4 bonds, nitrogen can have 3. If we had a nitrogen with 4 bonds on it, then it would have a positive charge. So if we have a positive charge on a nitrogen, something else will have to balance it out. So this would be considered a tertiary salt. Now this might be a little bit more advanced than some basic form of understanding chemistry, but it is important to note that a nitrogen bound to 4 different elements has a positive charge because it does not have all 5 of its valence electrons that it wants. So 1, 2, plus the 3 hydrogen, right? So when we have a nitrogen that is deficient, then it will go ahead and bind with an ionic bond to something such as this chloride ion. We're almost there, so please hold on to your seats. Let's see. One other miscellaneous group that we could look at is something such as a phosphate. This is a very interesting molecule because it allows not the common bond like carbon, where we'll see 4 bonds, but instead we can see 5. This is very important whenever we're looking at other sorts of organic chemistry, such as life chemistry, where phosphate is very important in terms of a mineral. So after the phosphate group, we'll go ahead and look at another one of our nice little organic compounds, which is sulfur. Not so nice, it smells very bad. And you would know this if you've ever had bad eggs or if you've had eggs rotting, because it is the sulfur group that smells, as well as the sulfur in your burps whenever you burp. So sulfur is very interesting because it can only bind to 2 groups. So this one specifically would be called dimethyl sulfide. You ask, what does that mean though? What does dimethyl sulfide mean? So let's explore further. We have 2 bonds to sulfur, correct? And we've established that each bond at the end of a line is a carbon. It is just shorthand, very simple, the CH3 bond, because we have the carbon bound to the sulfur and 3 adjacent hydrogens as well. So with our 3 hydrogens, we can see that there are 2 methyl groups, or dimethyl sulfide. So as a comparison of dimethyl sulfide to something simple, we can just go ahead and look at a methyl sulfide. So look at this. We can see there's 1. This would be called methyl sulfide. Is this group correct? No, it is not. The reason it's not is because we are missing a hydrogen here. Looking at a basic version of this would be hydrogen sulfide. Think about it for a second before I draw the structure. How would that be drawn? The way I would draw it would be like this, where it has its 2 bonds and adjacent hydrogens. If you want to write it out, you would write it such as H2S. You remember your carboxylic acid, right? Something similar to a carboxylic acid that is found in nature would be an amide. An amide, or amide, is effectively a carboxylic acid replaced with an amine in the hydroxyl group. We can also look at some other various structures, such as the nitrile. What is a nitrile? A nitrile is any group bound to a carbon with a nitrogen triple bonded. If we want to look further, it is a formality to draw the 2 electrons here, and we can see 1, 2, 3, 4, 5. Now our nitrogen's happy. There is no positive charge here. And this is a nice group because this can act as a very strong nucleophile. We'll discuss this further in a next series with nucleophilic addition. Another interesting structure that is similar to a carboxylic acid is the acyl chloride. The formality of statement acyl is the bound structure that has taken over for the hydroxyl group. As we know, amide or amine bound, the acyl group will be a formal halogen. So acyl can be any form of halogen. It can be a chloride, it can be a bromide. But as we keep going further, it becomes less and less possible for this to be bound directly onto a carbon because of the polarity and disparity of electrons from this carbon to the oxygen molecule. So if it was a bromide, what would we call it? We'd call it acyl bromide. It's very simple. Once you memorize these structures, you'll draw them a million times, just bound onto different compounds. Another formal structure here, now that we've established a triple bond for the nitrile, is the simple alkyne. Another way to see this structure would be the important part of understanding the alkyne is that it is simply a triple bond. So a basic alkane would be a single bond between carbons. Now that we've established the difference between alkyne and alkane, what's the intermediary? What would it be if we had a double bond? This looks like an equal sign, right? It would be an alkene. So the easiest way to remember it is A, E, Y. The reason that I give this is because I like acronyms or organization to understand functional groups and memorizing difficult substructures. So if we look at something and we see it has a single bond, what is the first letter in the alphabet? It is the A. So the next letter that would come would not be Y, it would be E, alkene. And finally, the alkyne is the last letter that would be in the alphabet. There are many ways to memorize these different structures, and definitely use your different methods because everyone is unique. However, I'm going to just show you some little tips and tricks that I have used to memorize this over the years. Another addition onto the carboxylic acid chain is called an ester. So an ester is effectively the same hydroxyl, right, with a group bound to it. It can be a methyl, it can be an ethyl, it could be a propyl. Doesn't matter what's bound to it. What does matter is that there is this consistency of a bound group, whether it be alkane or any other form of bound group to this oxygen here. So this is the ester. So with the ester group, we can look at something similar that I want to make a huge difference in your mind for, because these two will get mashed up together as one thought. It is the ether. Ether is an oxygen bound to adjacent carbons. In this case, it would be dimethyl ether, right? Because we have one methyl here and one methyl here. Just remember that it's ether and not ester. An ester is bound into a carbonyl system. An ether is alone. Even if we have something like this, this would still be considered an ether. The reason there is, as we look here, this is a ketone, right? That's not a carboxylic acid like this, where it's directly bound to the central carbon with the oxygen. It is alpha to the carbon. So this would be considered a methyl ketone. Another one that can be compared with the acyl chloride, which, as we remember, is just a chloral group attached to a nice little carbonyl, is the alkyl halide. It is simply any form of alkene bound to a halide. Yeah, chemistry's fun, remember that. Any of these can be an alkyl halide. One interesting group that I'd like to touch on is the benzene ring. Now you ask, what is the benzene ring? It is 6 carbons bound in double bonds where there is a hydrogen at each location. This is important because benzene is a very common player in organic chemistry, not only as a solvent, but just as a functional group itself. One common would be aniline. Aniline is also another form of solvent, as well can be used in organic reactions, as the amine group is very stabilized by this benzene ring. And it's also super easy to remember because aniline has the amine group on it, and at least to me I can see the ene, aniline, whichever way you want to call it. One other fun benzene group is the phenol. You may know it for throat spray, and it actually does smell exactly like that. Very toxic, so you want to be careful with this. However, it is also pretty simple to remember because of the ol at the end. So the ene and ol, very easy to separate those because most functional groups will have these little tidbits of information where you can see that. One final benzyl group that I would like to touch on So one thing that we can state is if this benzene ring is bound into a system, we could go ahead and just call this a phenyl group. This itself alone with the hydrogen there is called benzene. However, as a functional group, it is technically a phenyl. We will type that out for you. So this is a very crude understanding of chemical structures, and I hope you enjoyed my performance here for you today. If you have any interesting comments or suggestions for improvement on this, please let me know. As well, if you have any questions about organic chemistry, feel free to contact me at any point in time. Thank you.